Assalamu alaikum everyone. This is lecture 15 on digital control system. We are studying chapter 4, design of discrete time control systems by conventional methods. Today we're going to start the article 4.3, which is a stability analysis of the closed loop systems in the Z-plane. So from the classical control, we know that the stability is been determined by the Routh-Hurwitz criterion or Routh stability criteria, and we have formed the Routh table. Then analyzing the Routh table, basically the number of the sign changes in the Routh table, we try to find out the stability of the classical control system. In the digital domain, actually, we'll try to analyze the system and try to figure out whether the system is stable or not, or whether it is critically stable or not, as well as their gain range for which it remains stable. This kind of thing will be discussed. So basically, we'll be considering a system that is linear, time invariant, as well as a single input, single output, digital, and we have to also consider the closed loop system. So closed loop, pulse transfer function. So these are our criteria, basically for a linear time invariant, single input, single output system, and we'll analyze with the pulse transfer function of the closed loop system. Okay, so we can have a system something like this, CZ by RZ, that is output by input, equal to GZ 1 plus GZ. So we know that the denominator of the equation is called the characteristic equation. So we can say that our characteristic equation, we can also give it a polynomial Pz, which is characteristic equation is 1 plus Gz. Okay, and that should be set it to 0. Then you can do the analysis on that one. So this is one type of closed loops system. There are few other possible, and those are actually based on the location of the system. Okay, so now what we have to recall is that I think it was table 2.1. You'll see the other combinations, and accordingly you have to adjust your transfer function. In some cases you are going to find GHZ, and in some cases some other parameter will be also introduced. So bottom line is that based on different kind of systems closed loop transfer function, eventually whatever the denominator that you are going to get, that denominator will be your characteristic equation. We call this one as a characteristic equation. Okay, so now what is a stable system? So from the characteristic equation, this condition for the stability is roots of all. Notice all the roots should be there. We should emphasize on that. All roots of characteristic equation, or the closed loop poles, or closed loop poles, should be within the unit circle. Why unit circle? Within the unit circle, because we know that we have seen that we compare with our S plane with our Z plane. So we have seen that the entire left half of the Z plane is actually interior to our unit circle. So this is something that we have derived. And the right half plane is basically going to be, okay, so the right half plane will be external to the unit circle, and similarly the j omega axis that will be our on top of the unit circle. So if you consider the j omega axis here, and that should be same as the unit circle. Okay, so from all these criteria, we can say that for the stability, all the poles has to be on the right half plane. Similarly, for the unstable system, what we can deploy that unstable system, the definition is any pole outside the unit circle. So any roots or any poles of the characteristic equation or poles of your closed loop pulse transfer function can make outside the unit circle. Outside the unit circle. So that is the condition for your unstable system. So stable, unstability has been defined. Now next is coming the critically stable system. So for the critically stable system, the poles, if the pole lies at as j equal to 1. So poles, okay, so critically stable, So poles lie so we have to be careful how many pole we can allow. So pole lies at z equal to 1. That means uh, on the unit circle, then the system is called critically stable. Also, the system becomes critically stable if a single pair of conjugate complex poles lies on the unit circle. So also another condition is single pair of conjugate complex poles, conjugate complex poles, and lie on the unit circle. Okay, so lie on the unit circle. So what does it mean? The first condition says that if you have a single pole somewhere in the unit circle here or here, okay, so this is true. And complex one actually appear in complex conjugate. So if you have one here, the other one should be here as well. So then that is also true. So if this is happening, that is also will give us a system that will be critically stable. Now, so what will be the condition for the unstable system? So unstable system condition is if any multiple pole, if we have multiple closed loop pole on the unit circle. Multiple closed loop pole on the unit circle. So this is not for critical, this is for unstable. So what does it mean is if you have two pole in the same location or more than one pole in the same location on the unit circle, or even on the same location, multiple poles, in that case, system will be unstable. Why? Because if you look at from the point of view of the classical control, we know that multiple pole means something like this 1 by s plus a 2 square. Okay, so it means if you take it to the time domain, then you're going to see that it will be in t e to the power minus twice t. So this t term is actually making the system go to infinity as t goes to infinity. So this magnitude is also becoming infinity, tends to infinity. So that is why the system is becoming unstable. So it is also true for any number of values, and then it will be actually factorial n by s plus to the power n. Okay, so just even if you recall, if you don't know, then you can just review the chapter, I think chapter 2 of the nicest book. Okay, so if you have something like this, then this is what you're going to get. Okay, so bottom line is in critical, if there is a single pole in the Z in the unit circle, or a pole pair complex conjugate which appear in the complex conjugate, that can also be allowed, but multiple pole is not allowed. Okay, so this is a condition for the critical stable and the unstable. And the third condition is that closed loop zeros have no effect. So closed loop zeros do not affect the absolute stability. Do not affect the absolute stability. Okay, so hence they can be within or without, within or outside the unit cycle. So it doesn't make any difference where they are. Therefore, a linear time invariant single input, single output, discrete and control system, closed loop control system becomes unstable with the condition that if poles are outside the unit cycle, any pole is outside the unit cycle, and or condition is if multiple poles appear on the unit cycle, unit circle. So then the system is unstable. I mean, unfortunately, I'm saying some multiple times in cycle, but it will be actually in circle. So sorry for that unintentional mistake. Okay, now since we know that, let us try to solve one problem and check how to find out whether the system is stable or not. So example 4.2, and as you can see that closed loop system is given, and sampler is there. Then you have a proportional gain k, and you have a sample and hold, which is represented by 1 minus a to the power minus s by s. Then you have 1 by s into s plus 1. So basically, this is our plant. This is our sample and hold. This is just a proportional gain, or and now you have unity feedback coming. Okay, so this is the system that is given. So you can represent in the Laplace or in the Z domain, CS or CZ. Okay, so as we already said, in most of the cases we'll be combining these two and we'll be calling that as GZ. Eventually they will be multiplied together, or GS. Then you have to convert it to Z domain. So, and they're given that k equal to 1, even if it is not given sometimes, and you don't want to find out the range of the k, then also you can assume it by 1. So g of s is 1 minus e to the power minus s by s. Then you have 1 by s plus s into s plus 1. Okay, so this is, I think, example of the previous chapter, example. Okay, so example 3.7. So I'm just not going to go into the derivation, so I'm letting it for you. So please have a review of that one on g of z, which is the z transformation of 1 minus e to the minus s by s, 1 by s into s plus 1. So what you're going to get is 0.3679 z plus 0.2642 divided by Z minus 0.3679 into Z minus 1. Okay, so since we have to deal with the closed loop transfer function, so let's figure out what is Cz by Rz. In this particular case, since we have only one transfer function, we can just write it as Gz by 1 plus Gz, the one that we have assumed earlier. So we can easily find out the characteristic equation, which is 1 plus Gz. Should be equal to 0, and hence we can find that it is just a bit of manipulation will give you Z minus 0.3679 into Z minus 1 plus 0.3679 Z plus 0.2642 equal to 0. Okay, so if we do a bit of calculation, then we are going to find that it gives us Z square minus Z plus 0.6321 equal to 0. Now, if we go for the solution of the quadratic equation, then you're going to find out Z1 equal to 0.5 plus J 0.6181, and Z2 will be 0.5. They will appear in the complex conjugate, no doubt about it. It's a 0.6181. So in the Z, so in the Z plane, what you can see is that if it is a unit circle, you have 1 minus 1. Okay, so 1 minus 1. So we can see that actually 0.5, that is 0.5 somewhere here, and 0.61 somewhere here. This is one pole and this is another pole, so which is within the unit circle, and that is why the system is stable. Or mathematically, we can say that the magnitude of Z1 and magnitude of Z2 is actually lesser than 1. So within the unit circle, and the system is stable. System is stable. So we had a gain value K. So if you want, you can also prove or show that for K is greater than 2.3925. If you follow this criteria, so if the value of the gain is greater than that, then the system will become unstable. Okay, then the system will become unstable. Okay, so that one, I think in one of the example 4.7, we'll also try to show that how to derive that, or how to find the condition that gives this kind of thing. So this is a direct solution. Find out the location of the roots of the characteristic equation based on the defined area. But the methods that in general used is 3 methods are used. Methods of testing absolute stability. Okay, 3 methods are there. Number 1 is Shoup-Conn test, and then you have Jury test, and third one is bilinear transformation. Bilinear transformation. Along with that, the known Raoult's criterion. Raoult's criterion. So this one is complex, manipulation is required, and this one is also complex. Compared to these two, this one is actually relatively involves with less computation and easier to comprehend. So this one is not discussed in the book, and a small demo is also given on this one. So an introduction is given. So if you want, you can go about it. So basically, we will focus on the jury test for the stability criterion. So what the jury test says is that if you have a polynomial, you have to form a table, and after forming the table, you have to give some certain condition you have to figure out, and if those fulfill, then the system is stable. If the conditions doesn't fulfill, then the system is unstable. So let's start with the jury test. Jury test. Okay, the first thing is that you should have the polynomial or the characteristic equation. Okay, so this is our characteristic equation. So generally it is written as anz to the power n in this pattern, but somehow they have written in this way. Now, based on this characteristic equation, we have to actually form a table. So the table will be something like this. Row. So there we have to write the z to the power 0, z to the power 1, z to the power 2, z to the power 3, and goes up to the order of the z that we have, that is z to the power n minus 2, z to the power n minus 1, and finally z to the power n. So the coefficients have to be organized in how many rows there should be, that the number is given by twice n minus 3. This is what has been followed. So if it is a third, if your n is 3, the third order equation, so n equal to 3, so it will be 6 minus 3 equal to 3. So if it is 4, then 4, 8 minus 3 will be 5. So this is for third order, and this is for fourth order. So how many rows will be there? So eventually the total number of rows will be twice n minus 3. Okay. So now how the first row will be constituted? Or you give the row numbers, 1, 2, 3 goes on. The first one will be the coefficient of the 0, z to the power 0. So here actually you have z to the power 0. So it is an, then a n minus 1, a n minus 2, a n minus 3. And this is how it will go up to a2, a1, a0. The second, or even actually all the even numbers will be just the reverse of the first one, the odd ones. Okay, so it is a0, so it will be reverse a0, a1, a2, a3, then a n minus 2, a n minus 1, and then finally a n. So this is how you have to form the even rows. Now, what will be the next rows? So next row, say you'll be coming as B. So next row will be B, that is, say there is third row. So it has to be Bn. Then you'll have Bn minus 2, n minus 1, Bn minus 2, Bn minus 3, and then it will go up to B1 and B0. So one column is reducing, and then you have to alternate it, because we said that even one will be eventually whatever the reverse order. So B1, B2, B3, and then finally it will be B. Oh, sorry, it was my mistake. It will be, because it is one less, so it will be Bn minus 1, 2, 3, 4. Okay, so eventually it will be Bn minus 2 and bn minus 1. And now we know that it will be again one less in the fifth column because it is reducing by 1. So if it is bn, so it will be ending up with bn cn minus 2. So cn minus 2, cn minus 3, cn minus 4, cn minus 5. And then it will go up to eventually up to c0, one less. And again, the 6 will be alternate. Eventually, the last one will be twice n minus 3. And before that one will be twice n minus 4. And the previous one will be twice n minus 5. So we can write these 3 columns as in this pattern, that is P3, P2, P1, P0, then the even will be just alternative, reverse ordered. So P0, P1, P2, P3, and the last one will be Q2, Q1, and Q0. Now the question is, you may be asking how this table has been formed. So the formula for forming that one, BK, is a determinant, that is an by a0. As you can see, the first one. So this 2. Then you have the formula is a n minus 1 minus k divided by a k plus 1. So where your k values actually range from 0, 1, 2, goes on to n minus 1. So what is a bk? So basically b0, k equal to 0 means 0, b0 equal to an a0, then you have an minus 1 and a1. So now look at here, these two are nothing but the next one, that is these two. Okay, so but where it is placed, it is actually placed in the last one. So you have to keep it in mind. So if you, and for the next one, as you can see, the first 2 are not changing. That is, first column of the determinant is unchanged. The others will be changing. So if you take B1, then you have to take these 2. If you take B2, then the next 2. Okay, so this is how you have to form. So basically, if you want to find out the bn minus 1, then actually the first one and the last one you have to take. Okay, so this is how you have to deal with in the table. Eventually, the whole table will be formed in this way, but you have to keep in mind that the last one has to be 3 parameter, and the last row number has to be twice n minus 3. Okay, so this is how you have to follow. And once you fill up this table, so what will be the condition for a stable system? So the conditions for the stable system, the following condition you have to follow. First of all, number 1 is the value of an, magnitude of an has to be lesser than a0. So this is first condition that should follow. The second condition of the characteristic equation, you have to put z equal to 1, and if the magnitude of this one has to be greater than 0. And third condition is in the characteristic equation, you have to set z equal to minus 1, and then you have to check the value. So if value is greater than 0, it has to be greater than 0 for n, a even number of n. So if n is even, then this is what you then the value has to be greater than 0, and if n is odd, then the value has to be lesser than 0 for n odd. Okay, and fourth condition. So fourth condition actually you have to follow. First of all, the from the characteristic equation, the magnitude of the an has to be lesser than a0. Then pz, where z is tends to 1, has to be greater than 0. These two are straightforward. The other two, the third one basically conditional based on the value of n, whether even or odd. If n is even, then the magnitude has to be greater than 0. If n is odd, then magnitude has to be lesser than 0. And then last one is rest of the coefficients, that is bn minus 1 needs to be greater than b0. Then cn minus 2 needs to be greater than c0. So all the rest of them, all the rest of the table contents, the highest one has to be greater than the lowest one. So that in our case, the final one was q. So q2 needs to be greater than q0. So this is what we have to follow. So if all these four conditions is valid, all four are valid, then we can say that system is stable. System is stable. Okay, so now look at one particular example. So forming this table at some times is slightly difficult. So that is why an alternative table is also being proposed. And eventually, we don't need the entire table, just the magnitude of this one, the first and the last one. So to find out the table, even another alternative one is given, and that one is will be available in your example 4.3. So just have a look at that one. We eventually will be following that one in example 4.4, but we are not detailing because of the shortage of time. We are just giving. Okay, so say we have pz given. Characteristic equation is z to the power 4 minus 1.2 z to the power 3 plus 0.07 z square plus 0.3 z plus minus 0.08 equal to 0. Okay, so this is a characteristic equation given. So this is our coefficient is a0, a1, a2, a3, a4. Okay, so first condition is given as the an, magnitude of an should be lesser than a0. So as you can see here, magnitude of an is 0.08, and which is definitely lesser than magnitude 1. So this is true, satisfied. Number 2 is pz, where actually we have to find out p1. So if you put it, then we find that 1 minus 1.2 plus 0.07 plus 0.3 minus 0.08. Now the magnitude of this one is becoming 0.09. 0.09, and definitely which is greater than 1. So this was the second criteria, so that is also true. Okay, so third criteria is that pz or p minus 1 should, it depends actually n, if it is even, then p minus 1 has to be greater than 0. Okay, so in our case, this is the case. So you just put the value and do the calculation, and you're going to see that the magnitude is becoming 1.89, which is greater than 0. And the third condition is also true. Okay. Now the fourth condition is the rest of the coefficient. Now you have to calculate the rest of the coefficients. Now the alternative method that we have shown instead of writing the table in detail. So what they have done is to find out the table, they have modified the table a bit. So row. So the first row is been actually divided in such a way that Z0, Z1, Z2, sorry, Z to the power 2, Z to the power 3, Z to the power 4. So what they have done is instead of writing the entire row, they have written the first one, 0.08, 1. And based on that, they'll try to calculate the B, the last B, that is B3 in this particular case, because we have AN equal to A4. So the B will be a 1 lesser, so it will be B3, and the C will be C2. In this way, it will be happening. Okay, so for the B3, we have to do this one, that is 1 in the reverse order. So 1 minus 0.08. And then you can just find the value of the determinant. And you'll see that the magnitude will become something like this. That is minus 0.994. So minus 0.994. And similarly, because the first row is not going to change, first column, so 0.08. I'm not sure why, but nowadays this Microsoft whiteboard creates trouble. Okay, so it will be minus 1.2, then 0.3. And that will give us a value of B2. And if calculate, then you're going to see that 1.176. 1.176. Then again 0.081. The next value of the determinant will be 0.07. 0.07. Okay, so that will give us the value of B1, and that is minus 0.0756. Okay, so minus 0.0756. And then you have 0.08 by 1, and then the last one, that is 0.3. And then you have minus 1.2, and that determinant will give you the value of B0, and the B0 is nothing but minus 0.204. So minus 0.204. So similarly, you so this is basically your 1 and 2 column, column 1 and 2. And rest of them gradually you can fill it up by looking at this sphere. So instead of writing the whole rows here, just write the ones needed to find out the corresponding coefficient in the reverse order. This is B3, B here. So finally, since you know this B3 And B0, you can see that it will be coming here as B3, that there is minus 0.994, and B0 is in the reverse order in the next line, so minus 0.204. And then you one less, so basically here again you will find minus 0.204 and minus 0.994. So based on that, you are going to calculate your C2, and which is happened to be 0.946. So this is 0.946. Okay, so actually when we started, let me actually finish, then at least one example, if we cover totally, that will be beneficial, minus 0.994. It is not changing, as we already said. And the next one will be coming as minus 0.0756 and 1.176. Okay, so that will give us C1, and the magnitude of the C1 is minus 1.184. Minus 1.184. And the last one will be calculated as, if we proceed with the same first column, 0.994 minus 0.204. Okay, and then you have 1.176 and minus 0.0756, and that will give us the value of C0, that is 0.315. 0.315. So we know that in the last column, that is twice n minus 3, we should have 3 values. So we already have 3 values, C0, C1, and C2. So this is your 2 and 3 and 4, sorry, 3 and 4, and the fifth one will need 3 values, that is 0.946, 946. Then you have minus 1.184. Then you have, I think I need to change in the nib of the pen. It's too much decayed. So that is why this kind of problem I'm going through. 315. Okay, now the 3 conditions that we should look for is, first of all, magnitude of Bn, that is B3, should be greater than the magnitude of B0. So only magnitude. Similarly, C2 maximum value should be greater than C0. So are they true? That is here. We can see that 0.994 is definitely greater than 0.204. So it's true, as well as this one, that is 0.946 is greater than C0, that is our 0.315, I think. Yes, 0.315. So all satisfied, So the system is stable. Okay, let me stop here with this one, and we have to cover a bit more in this one. So maybe in the part 2, we'll start in the part 2 of the lecture, inshallah.